Hello and welcome to an introductory lesson on solving linear trig equations. Now we've just come from a section of our course where we've done a lot of work with trig identities. And it's important to realize that identities and trig equations are not the same thing. Well, trig identities are equations, but not all equations are identities. And what I mean by that is we took a look the last few days at statements like this, where we've got sine squared of an angle plus cos squared of the same angle is equal to 1, and we picked a bunch of different angles, all kinds of numbers for that angle. Let's if we talk degrees, let's say 74 degrees. The sine of 74 degrees times itself plus the cos of 74 degrees times itself, it's always equal to 1. And so any theta angle makes this a true statement. And that's why it is considered a trig identity. However, other equations are not true for all angles. For example, if we do something as simple as sine of theta equaling -1. Well, that's an equation, but that is not true for all angles. You put all kinds of different angles in there, you'll get the sine value not being a -1. And if we graph this just for the first cycle of sine, we know that if we have 2 pi radians there, this would be pi over 2 or 90 degrees. And that is in fact where sine is equal to 1. And there's only a single angle that makes this equation true in the first full cycle. Of course, we get more values of 1 as we add period lengths to that, but only certain angles make this equation true. So, the difference between an identity and an equation. So for now, what we're going to do is launch off talking about other trig equations. Solving a trig equation is very similar to solving an algebraic equation in the way that we have done before. We try to isolate our unknown. Here we've got 9x squared minus 97 is equal to -16. What value makes that equation true? We're trying to find the mystery number that would make this side a -16. And so we've been taught to use our algebraic skills to add 97 to both sides. So that is an 81. And if we divide by 9 on both sides, and so we've got these algebraic skills, and solving a trig equation is going to be very similar as well. And so when we talk about taking the square root, we have to remember that there's both a positive and a negative answer to that. And so x could be a +3. +3 squared times 9 minus -97 is equal to -16, but -3 also works. And so we've done a lot of that. But trig equations, we're solving for the angle that makes it true. And so we do a lot of this isolating, but then we have one more step. For example, sine of some mystery angle plus 3. So that value is going to equal 2. And we want the answers from 0 to 2 pi radians because, of course, the whole cycle cycles again, and there's an infinite number of answers. But in the first full cycle of sine, and what we can do is employ our strategy of algebraic skills where we'll subtract 3 from both sides, and we get the sine of theta equaling -1. And now we're not done. We've isolated our trig ratio, getting it equal to a number, but we know that if we draw a quick sketch, where is sine equal to that -1? Well, we know that that is an angle of 3 pi by 2. And so only the angle of 3 pi by 2 in the first 0 to 2 pi radians makes that equation true. So one last step, we isolate it down to a single trig ratio equals a number, and then we will be solving for what angle gives us that number. So something as simple as this. Now this one is an example where we will get an exact value out of this equation. We would not need a calculator to do this problem. The next one we'll get an approximate value out of that. And I like to break it down into steps 1 through 4. And I know that sometimes you'll be thinking, why do I have to do this step? This step is so simple. I wish I could just skip this step. And I would ask you to bear with me because we're going to be doing more and more complicated equations as we go through. And one of the steps that didn't seem to be so useful now will be very useful later, I promise you. So step 1, manipulate the equation until one trig ratio is isolated. Get it down to sine equals a number, or cos equals a number, or tan equals a number, that kind of thing. So we're working with root 2 times the sine of theta plus 5 equals 4. So let's subtract 5 off of both sides. Whoop. So 4 minus 5, we get the root 2 sine theta is -1. Let's divide both sides by that root 2. We get, oh, when is the sine, what angle gives me a -1 over root 2? Now, in the past, we've skipped right to cast rule, but I would ask you to just consider for a second where it is in this first cycle of sine that we're calling for these answers. Now, -1 over the square root of 2, if you put that into your calculator, that is approximately a -0.7. And so -1 is here, +1 is here, a -0.7 might be about there. And so what we're doing is we are busy looking for the two angles that make sine equal to a -0.7, that is negative. And so here's my angle. And here's my angle. There's two answers. We know that it is something a little bit bigger than pi radians, so a little bit bigger than 3.1-ish, a little bit smaller than 2 pi, and certainly 3 pi by 2 in the middle. Get the decimal value for that. We should be able to ballpark our answers. And again, I know that's a step that you probably don't like doing. It'll reinforce the graph of sine, but more importantly, it tells us how many answers we're looking for. In a simple cast rule question like this, we are always looking for two answers, but again, when we get into more difficult double angle problems or quadratic trigonometric problems, we will have more than two answers to look for. And doing a quick graph sketch will give us an idea of how many we're looking for and about how big they are. And so we know that if I'm going to solve sine theta equals a -1 over root 2, I'm always looking for my reference angle. And for that, if I was using a calculator, I would do the sine inverse of the positive value, the absolute value of this, because I'm looking for the related acute angles. And acute angles have sine ratios that are all positive. And so on my calculator, I could get some rotten rounded decimal here, but I also know that I can find this angle. I have a 1, 1, root 2 triangle with a pi by 4 or 45-degree angle that will be my reference angle. Sine will be opposite over hypotenuse. And so my reference angle is going to be a pi by 4 angle. Once I have found my reference angle, then we will use cast rule to remind us of the quadrants for which my ratio is negative. So I'm asking myself, where is sine negative? And I know that sine is positive in my first two quadrants, negative in my third quadrant. So there is my larger theta angle that makes my original equation true. It has a pi by 4 reference angle, and so this angle is a half circle plus another pi by 4. Well, there's 4 pi by 4s in a half circle, and so this would be pi plus pi by 4, so 4 pi by 4s, or you can jump right to the 5 pi by 4s. Similarly, cast rule also reminds us that this could be a fourth quadrant angle. There's my theta angle into the fourth quadrant with a pi by 4 reference angle. And so I know that theta will be 2 pi minus that pi by 4, and I can get my common denominators. Or I can think that if there's 4 pi by 4s in a half circle to reduce to pi, then there'd be another 4, so 8 total in a full circle, 8 pi by 4s for 2 pi radians worth of angles. And so if I am 1 short of a full circle, then this is going to be 7 pi by 4s. And so my two answers that make this original equation true, if you put 5 pi by 4s in here and plug it into your calculator, you'll get a 4. Or if you put 7 pi by 4s, plug it into your calculator, you'll get a 4. And that is one way to check your answers. This was an example of getting exact values where you wouldn't actually need a calculator to be able to solve that. This one, however, we have got some decimals involved in here. We don't have any special triangles. And so my step one was to isolate my trig ratio to be equal to a single number. So let's kick out this 7.6. We will take 3 cos x. We will, sorry, getting distracted here. We'll subtract that 7.6 off of our both sides, getting us to
Martin, you have a call on 701. That's Martin, 701.
A negative 2.6, and then we'll divide away that 3. Now, this you can actually put into your calculator, or if you want a rounded decimal, then carry at least 4 decimal places of accuracy to have any kind of accuracy in our angle. And so here I have isolated my trig ratio, cos of an angle equals a number. Now, step 2, remember, was to sketch. And so let's sketch cosine. Cosine starts at its maximum of 1, ends at a maximum of 1, with a minimum in between, and its axis points right in between those values. And so a quick sketch of cosine and a ballpark of our answers. We're looking for negative 0.8667, so something very close to negative 1, maybe in about there, 8667. And so I'm looking for two angles very close to 3 pi by 2. Now remember, we're going to get decimals out of this, so 3 pi divided by 2, 3 pi by 2 as a decimal, 3 times pi, 3.14159, divided by 2, comes to about 4.7. So I had better get an answer a little less than 4.7 and a little greater than 4.7. So there's one of my answers, there's another one of my answers, flanking the 3 pi by 2 in the, or sorry, pi. My goodness, I'm thinking of the last question. So again, I better ballpark my answers here. This is pi radians, not 3 pi by 2, and pi is 3.14159. I had better get answers just below 3.1 and just above 3.1. Okay, step 3 is to find my reference angle. Step 1 was to isolate cosine of x. Okay, so find my reference angle. I'm definitely not going to have a special triangle for this. So the cosine of my reference angle, I will use the positive ratio. So my reference angle, I'll do the cos inverse for that positive ratio. Again, positive ratio to get that small related acute angle. If I put the negative in there, it will give me my first answer, but then it'll give me this one. But then I won't have an ability to get the second one because I need my reference angle. And so the cos inverse comes to 0.52 radians, so a little bit more than half of a radian big. Remember, we're in radians, so we're not going to be doing degrees. So now we use cast rule to put our reference angle into the appropriate quadrants. And we were originally negative, so where is cosine negative? And so cosine, CA, it's two positive quadrants, so cosine is negative in this quadrant, and so I put my 0.52 reference angle there, and so my theta angle, that makes my original equation true. Actually, it's not theta, we're talking x as our variable. And so my x angle will be pi radians, or a half circle, minus that 0.52. And so we get pi minus 0.52 being 2.6, which was just a little less than 3.1. So we are heading in the right direction. And then here is another x angle with a 0.52 reference angle in my third quadrant. And so this angle that makes my original equation true would be pi plus my 0.52. And pi plus my 0.52 is a 3.66 or a 3.7 approximately. These are approximate answers. And so we find our two values, a 2.6 and a 3.7, are the radian size angles that if I put it here, plunk that into my calculator, I will get a 5 or close to a 5 because we did round, so we've introduced some error. So those are two examples of two very basic linear equations. And what I would like to do is to give you an example of one where you've got to do some work before you can get to cos equals a number, or sine equals a number, or tan equals a number. And so you'll have some algebra to do before you can launch into the next steps. And so if we take our sine of x plus 4 is equal to the square root of 2 times the cosine of x, we are charged with isolating a single trig ratio equaling a number. Well, right here is my compound angle formula, or a situation that would have two angles added together for me to use my compound angle formula. And so I know that the sine of the first angle times the cos of the second plus the cos of that first angle times the sine of that second is equal to root 2 times the cosine of x. And in trig identities, we only ever worked with one side of our equation, but in trig equation solving, again, we're back to an equation, just like we solved equations algebraically. Where was that? We always work with both sides of the equation. And so this one, now what we're going to do is we're going to clean this up a little bit. I know the value for the cos of pi by 4. And so the sine of x is going to be multiplied by a 1 over root 2 as the cos of pi by 4. And the cos of x, sine of pi by 4, is also 1 over root 2 from our special triangle, is equal to root 2 times the cos of x. And if I have the same constants in my denominator, the square root of 2 and the square root of 2 here, I could multiply both sides of my equation by a square root of 2 in order to be able to simplify this a little bit. And so I've got 1 over root 2 times sine times a root 2 and 1 over root 2. Remember, that's not my angle. I've got cos of an angle times the 1 over root 2. I could in fact put that in front as 1 over root 2 times the sine of x. And so I will have root 2 over root 2 sine of x. And you know what? We're very comfortable having that in front, so let me put that in front. Root 2 over, so root 2 times this fraction would be root 2 over root 2 times the sine of x. Plus, again, if I've got this 1 over root 2, could be shown in front of cos of x, and I'm multiplying in a root 2, then it would be root 2 over root 2. And of course, those are just ones, and I'm going to simplify those away. And the square root of 2 times the square root of 2 back here would be the square root of 4, which of course can be simplified to a single value of 2. And so I get sine of x plus cos of x is equal to a 2 cos x. All right, well, I've got cos on both sides, so let's subtract cosine from both sides. So I've got the sine of x, 2 cos x minus a cos x, so I've got two of them here and I'm taking away one, and I get the sine of x is equal to a single cosine x on this side. And I'm looking at that going, when is the sine of x equal to the cos of x? And I would encourage you to actually type this into a graphing calculator, put y is equal to the sine of x on it, and put y is equal to the cos of x into it as a separate equation, and find out where those two lines intersect, where they are equal to each other. Because you can visually see it on a graph, where is sine of x equal to the cos of x. But in order to get us where we want to go, which is to isolate a single trig ratio, what we actually can do is divide both sides by the same value. That keeps our equation in balance. And if I choose to divide both sides by cos of x, then I turn it into a single trig ratio of, hey, tan of x equals 1? Oh, well, that's a single trig ratio equals a number. And so because this is our teaching note, let's remind ourselves that we can divide both sides of the equation by cosine to isolate one, and that was our goal, trig ratio. Okay, so step 2 was to draw our trig expression here. Great review of how to draw tangent from 0 to 2 pi. Remember, you can link it to sine in terms of how does sine start. Sine starts with a 0, ends with a 0 in between. And normally sine would go up to its maximum. Tangent, right in between at pi by 2, has its first asymptote, first undefined value. At 3 pi by 2 has its second undefined value. At pi by 4 increments, it will have its ones and its negative ones. And the tangent to pi by 4, tangent is a generally increasing curve, and so the tangent of pi by 4 is 1, and that is one of our answers to this trig equation. Let's put our ones and our negative ones on here. And so if we can read them right off the graph, we actually don't have to go to cast rule. Where is tangent 1? Well, it's here at pi by 4, and then again here at 1 pi by 4, 2 pi by 4s, 3 pi by 4s, 4 pi by 4s. This would be 5 of those pi by 4s. And so if you can, read the angle values from your sketch. You are done. There's no need to go to steps 3 and 4. And so x, the angle that makes this true, you can put a pi by 4 here or a 5 pi by 4 here, plug it into your calculator, and you will get the same value as the right hand side with a pi by 4 or a 5 pi by 4 in it. And so those are just a few examples of very basic trig equations, an exact value trig equation where you wouldn't need a calculator, a approximate value of your angle sizes where you do need a calculator, and then one where you have to do quite a bit more work to get down to a single trig ratio equals a number. And so please don't skip step number 2. Again, I promise you that it is going to become very useful in the future. And so now what I would ask you to do is to dive into the practice problems that I will provide for you, and we will move on next day to linear trig equations, but perhaps in here we might have cos of 2x or cos of 3x or cos of x over 2, where we've got a d value in our equation that changes the period length. And then we will also look at quadratic trig equations and solving them.